Hey everybody, welcome back. Mr. G here again. Welcome to the next lecture in the series for Tech 101 Electric Circuits. Today what we're going to be talking about is a theory referred to as the maximum power transfer theorem. And what we're going to be looking at is over the next few weeks a number of different theories, starting with this one. So again, this is maximum power transfer. Information can be found in our textbook, Principles of Electric Circuits, Buckla and Floyd 10th edition, chapter 8-7, if you're looking for it. So, in the last lecture, we looked at power in resistors. So, maximum power transfer has a lot to do with the lecture before. So if you didn't catch the lecture before, look for the video on power in resistors. So what is maximum power transfer? Well, let me just explain something. Again, this picture that I have here of an old stereo system connected to a speaker, this is kind of the best visual concept. We have a stereo system which consists of components that make up a power supply and the amplifier and all that kind of stuff inside this box. Connected to it is a speaker, which is a load. What we want to do is we want to get the most power transferred from this box to the speaker. That would make our stereo the loudest that it actually could be. So again, we want to be able to take as much power from the stereo and transfer it to the load. And that is a point at which we call maximum power transfer. Being able to take the most power, so that's that energy, and transfer it to the load to get the loudest sound that we can in this example. So what we're going to do is we are going to look at a basic circuit. So I'm going to really simplify it down, and we're going to go with black box theory. So our stereo translates into something very, very simple. It looks like this, where we have a power supply and some components that give us what's known as a source resistance, RS. Then we get that and connect it to our load. So in this case, the load is the speaker, RL. So inside the speaker is a voice coil which produces a load or a resistance on the amplifier. So we'll look at it like this. So we can take everything that is in here and represent it as one resistance and one power supply, so voltage of the source. Then we are going to take the speaker and we are going to translate that and put it into a single resistance that is connected to our amplifier. So the idea is being able to transfer as much power here or from here into the load. That's when we find maximum power transfer. So what conditions have to be met in order to transfer as much power that's being generated into the load? So what we're going to do is we're going to do a series of calculations. I'll plug in some values, and by experiment we're going to figure this out. So here we go. Alright, so what we're going to do is we're going to create a circuit. So again, just black box theory, one resistor, one power supply, so that represents the source. And then we have the load resistor. So in our example for the stereo, again, that's the speaker being connected to the receiver or amplifier. So I'm going to plug in some values here just so we can, so we can do some math. So we're going to say that Vs, just for fun, is 10 volts. Rs, we're going to say, is 100 ohms. And what we're going to do is we are going to replace the speaker with different resistances and find out which one will actually get the most power to the speaker. Once we do that, that will become the solution for maximum power transfer theory. So what I'm going to do is I'm just going to list a bunch of resistors down the side here that we're going to swap out for RL. So just think of it as we are changing the speaker on our stereo. So RL, and then we're going to calculate the power for RL. And once we get the largest power, that is maximum power transfer. So let's just start at 25 ohms. We'll go up to 50 ohms, 75 ohms. We'll go 100 ohms, 125, 150, 175, and 200. And we'll see which one of these speakers actually gets the most power from the source to the speaker. So in order to calculate the power, what we're going to use is a couple of formulas. The first one is based on Ohm's law. So we're going to find the current through RL is based on the voltage at the source divided by RS plus RL. So that's just Ohm's law. So this is our total of the resistor. You should recognize that by now. And then we're going to say that the power in RL is equal to the current in RL squared times RL resistance. So that's the version of the formula that we're going to use. So we're going to calculate the current for each one of these and the corresponding power and put the power. So just to keep it easy, I am going to write down here the current for each one. So IRL. So we're going to find IRL, we'll write that down, and then we'll plug that value into the power formula and get the power. And again, what we're looking for is the largest amount of power that we can achieve. So got out the old trusty calculator here. So we'll go through the currents real quick. Again, it's the same formula. The only difference is we're going to be changing RL in this case. So IRL is 10 divided by RS, which is 100, plus 25, so 125. So this works out to be 0.08 amps. The next one's going to be 50. So we got 10 divided by 150. we got 0.067 amps. And then we've got 10 divided by 175. 0.057 amps. 10 divided by 200. 0.05 amps. 10 divided by 225. 0.44 amps. Again, all I'm doing is applying this Ohm's law type formula. We got 10 divided by 250. 0.0, it's a 0 there. 0.04 amps. And 10 divided by 275. 0.036 amps. You'll notice that the current is dropping. Why? Because we're upping the resistance each time. So we got 300. So 10 divided by 300. So those are the currents. Again, just using this Ohm's law formula. So 10, that's our voltage supply, divided by the total resistance of the circuit, which is RS, which is always 100, and then we're changing RL for each case. And as RL goes up, the total resistance goes up, therefore the current falls. So now what we're going to do is we are going to swap out this current into this formula with that RL attached and find out what the power is for RL in each case. So in the first one we have 0.08 amps squared times 25. So we have 0.16 watts. So the next one, I have 0.067 squared times 50. And this becomes 0.22 watts. The next one, 0.057 squared times 75. 0.24 watts. So we're going up with the power so far. Next we have 0.05 squared times 100. And we got 0.25 watts. Then we got 0.044 squared times 125. 0.242 watts. See what's happened here? We've come to 24 watts, or 0.24 watts, then 0.25 watts, and now we're back down to 0.242 watts. So now we're going to go 0.04 squared times 150. 0.24 watts. 0.036 squared times 175. 0.227 watts. 0.033 squared times 200 equals 0.218 watts. So, if we keep the same stereo and swap out the speakers, you can actually see that we get to a point right here where this power is larger than any of those and larger than any of those. So if we made a little graph, so this is the power of RL versus RL, you'll see that the power actually goes up to a maximum point and then starts to fall again. That maximum point is what we refer to as the maximum power transfer. So where does that happen? Well, at this circuit, it looks like it happens at 100 ohms. So in this particular circuit, it looks like it happens at 100 ohms. Now, just to be sure that we just didn't luck out on something, let's try this. I'm going to stick a couple of values in here. I'm going to do a calculation for 98 ohms and another one for 102 ohms. So 100 ohms is right in the middle. Okay, so 100 ohms. So what I'm going to do is just kind of narrow it down. So instead of a big jump from 75 to 100, I'm actually going to go from 98 to 100. And instead of a big jump from 100 to 125, I'm going to go from 100 to 102. So let's just plug in those values. So again, we need to figure out our current. So for 98 ohms, so it's 10 divided by 198 equals. So our current is I is equal to 0.0505 amps. The next one at 102, again we're going to do the same math, 10 divided by 202. And here we have I is equal to 0.0495 amps. So let's just take those values and we will find our power calculation for those. So now we're going to put it into our power formula. So 0.0505 squared times 198 equals something went wrong in that calculation. Let's try again. 0.0505 squared, there we go, times, oh yeah, that's right, 98, it is 98, equals 24, so we got 0.2499 watts. Let's do the other one here. 0.0495 squared times 102, 0.24992 watts. So here again, 0.2499 watts, 0.2499 watts. Both of those are less than 0.25 of a watt. So we can safely conclude that 100 ohms is the point where we get maximum power transfer. The power rises up to that point After that point, the power falls. So notice one thing. Where does maximum power transfer actually happen? So, maximum power transfer actually happens at the point in the circuit where RS is equal to RL. So whenever your load resistance is equal to your source resistance, when the load resistance is equal to the source resistance, we achieve maximum power transfer. Here's the mathematical proof. If I went with a value smaller than 25 ohms, this will continue to go smaller. If I went with a value bigger than 200 ohms, this value will continue to go smaller. It maxes out when the load resistor is equal to the source resistance. So maximum power transfer of any circuit happens when the load and the source resistance are equal. So that is when we get the maximum amount of power being transferred to your load condition. So if we go back to our initial scenario here. So with this initial concept, in order to get maximum power to our speaker, the load resistance and the source resistance must be equal. So in a home stereo, typically we have 8 ohm speakers. Will match an 8 ohm source resistance inside to achieve maximum power. If these two are not the same, we will not be achieving the loudest stereo that we can get. So we want the loudest stereo system. We match the speaker to the stereo. So again, maximum power transfer happens at one point, and that point is when RS is equal to RL. So again, if you want some more information, go to chapter 8-7 of the textbook. I hope this helps. Until next time, everybody stay safe. Take care.